have one member of the committee which is connected online. Diane, if you have any connection problem at any moment, just let us know. Just tell us and we'll try to fix it. All right? Raul, we have about 50 minutes for the presentation, so we can start.
Okay. Okay, so thank you all for being here under these weird circumstances. And thank you for the people also attending online. So yeah, this is my PhD thesis defense, which is titled Exploiting the Interplay Between Visual and Textual Data for Scene Interpretation. And this PhD has been developed under an industrial PhD program, which means that it has been developed between university, in this case this lab, the Computer Vision Center, and a company, in this case Eurecat. And the idea of industrial PhD is to work on applied research that has a direct application in products, right? And that I really like researching on topics that can have a direct impact in our daily life. So my thesis directors from CBC has been Dimosthenis, Karatzas, and Josep from here from CBC, and Jaume Giver from Eurecat. And we have been working all together on the different topics I'm going to present today. And yeah, it has been a pleasure working with you. So let's get into it. In here we see an image showing a scene. And we can see that it's an image of a mountain in a sunny day with a sign in the foreground. And our computer vision community has spent many time working on algorithms to understand these images as humans do. But together with this image, we can have other information. For instance, in this image, we have some text in the image from which we can know the altitude of the mountain in meters and feet. And we can know that also the image is taken in LCamp, despite we might not know where that is. And we could even have some associated text to this image because maybe it appears in a newspaper or in social media. In caption, perfect spring ski day. So from it, we can also know that the scene happens in a ski day and during spring, right? And we could even have more information like the location where the image was taken. In this case, Aspen ski resort is located in Aspen. So in this PhD thesis, I work with images with some other associated information, specifically text. And I work in different tasks that require the joint processing, the joint interpretation of both data modalities. And in one of the chapters, I'm also going to work with images location. So that's why I want to start this presentation introducing the kind of data we are going to work with along the different chapters of this thesis. First, we can have image and text in different compositions, and I want to classify this. First, we can have text in images, which means that the text appear in the image content. And there, I want to distinguish between handwritten text or matching print text images, where text appears in the foreground, and scene text images, where text appears in the image integrated with other visual content and not necessarily in the foreground. And also, we can have text associated to images, where the text does not appear in the image content, but associated to it. And we can distinguish between different text types there. We can have articles, where are long text related with the image content. We can have captions, which are sentences generally describing the image content, or we can have tags, which are individual and independent words related to image concepts. So regardless the type of text we have, it can have different semantic relations with the image. So they can have a synergetic relation, which means that the image and the text carry the same semantic meaning. They can have a complementary relation, which means that the semantics of the text and the image complement each other to build a global context. Or they can have a not relation, for instance, a random text. So I wanted to introduce these different image and text relations because during the different chapters of the thesis, I would be dealing with different type of image and text compositions and semantic relations. So it's relevant to have this in mind. So now I'm going to introduce the research questions I set in this PhD thesis that also serve as an outline of the thesis itself and of the presentation I'm going to do today. So first, work with a syntax, and we are going to see first which visual features a net trained to recognize text in images learns, and then we'll see if we can train a neural network to translate text styles between syntaxed images, learning from a single image, I would add. And that will be the first chapter of the thesis. In the second one, we will be dealing with social media data consisting on images with associated captions, and we will see how we can exploit those captions as self-supervision to learn visual features, which we will apply to image retrieval. And also we will see which applications learning from social media can have in social applications or in products, which interesting applications we can have with this data. In the third chapter, I'm going to deal with an additional modality. So we will be having images with associated tags and also geolocations. And we will see which challenges that comes with. So first we will see which method is the best one to learn with images with tags, using the tags as supervision. Then we will see how location and visual information can be exploited together for image tagging. And we will also see how we can train an image retrieval system to retrieve images related to a given tag, to a given word, and next to a given location. Finally, in the last chapter, we will be dealing with social media posts consisting on images with associated text, which are susceptible to contain hate speech. And we are going to explore if we can jointly analyze images and in a multimodal hate speech detection model. Okay, so those are the research questions I have set for all my thesis. And now I'm going to start with the first chapter, dealing with syntax, and with the first research question. So at the beginning of my thesis, and that was like 2016, the state-of-the-art pipeline for object segmentation were fully convolutional networks, right? Object segmentation basically is a task which consists on finding which pixels in image belong to objects, and fully convolutional networks were introduced as a powerful method to do that. And we propose to use that same nets for text segmentation. So we train one of these FCNs with Coco text, where we have ground truth text mask to find the pixels in an image that contain text, right? So this network was outputting level the input image, and those maps turned out to be pretty accurate, right? They were detecting different kind of text, and we found that they were detecting that this net was detecting text of different shapes, different rotations, and it was even detecting text written in alphabets where that the training data didn't contain. And researching on that, we find that it was also detecting as text hieroglyphics or other kind of textures that have a similar structure as text does, right? And that's not that strange. Actually, humans, we do a similar thing to recognize text. So for instance, we recognize as text alphabets, scripts that we might not understand, but we can still imagine those are text, right? So at the end, this text FCN is doing the same for detecting text in an image. So the state-of-the-art pipeline for text detection by that time consists on a object proposals method, actually text proposals specifically, followed by a word classifier. So the object proposals method propose many regions in the image that were susceptible to contain text based on very simple cues. And then the object, the word recognizer, had to detect which ones of these regions actually were containing words. And one weakness of object proposals method is that they were proposing regions, even regions outside text areas, right? Let me see if this works. Yeah, even regions outside text areas. So what we propose here is to use the maps, the text probability map provided by the text FCN to suppress all these regions that were outside textual areas. And the result of that is that we end up with much less regions that have to be evaluated by the word recognizers. So this method results on better results when we analyzed with the word recognizer a limited number of proposals, and also on an efficiency boost of the whole algorithm when we analyze all the proposals, because we have to run the word recognizers for few of them. This was joint work with Dena Basazian, who also graduated from her PhD here last year in CBC, and it resulted in 2 publications with her. So yeah, also pleasure working with you, Dena. Okay, so let's go with the second research questions of this chapter, and that is, can we train a neural network to transfer text styles from text images, learning from a single image, I would add. So, a neural style model trains an image transformation network to transfer the style from a source content, to transfer the style from a source style image to a source content image, preserving the image content. What that means? That means that we want to generate an image that has the same content, which applied to text means the text transcription as the source content image, but with the style which applied to text means the shape of the letters, the colors, the kind of stroke it has of a source style image. And this works by training an image transformation network to generate an image that shares high-level features with the source content image and low and mid-level features with the source style image. So we train this network and we generate an image that has the source text style along all the image, and then we use the maps computed by the text FCN I was explaining before to transfer the style only to textual areas. So after this model, we propose an end-to-end model, which learns to do both tasks, style transfer and at once. So we get the image that has been stylized by a pre-trained style transfer network, and using the Cocotex ground truth mask, with only to the textual areas, network mean square error loss. And this end-to-end model ends up having similar results as the previous pipeline. And actually, we get quite good results from it. So here we have on the left the original images, on top the target text styles, and in the second and third column, the generated images. So as you see, we get that preserve the original text transcriptions, but with the new target styles. And we can think about many applications this can have, but we experiment with one, which is data augmentation. So basically, if we have a data set consisting on these original images for which we have ground truth, we can add to that data set the new generated images, so the diversity in our training data. And that's what we do. We apply this to a standard text detection data set like IGDAR and COCO. And we standard text detection on the plain data sets and on the augmented data sets. And yeah, we see that the style transfer is an effective data augmentation method, and the text detector trained on those augmented data sets achieve a better text detection performance. We also apply this style transfer method to other types of text. For instance, here we apply it to matching print text. And you see that also the generated text preserves the transcriptions, and we get the styles that are in between the original style and the target style. And we also apply it to handwritten text, which seems a more difficult task. And still, we are getting text with the original text transcriptions and with a style that is pretty similar to the target style. We can also apply this in a cross-modal manner. So, for instance, here we are stylizing matching with a syntax font, in this case this Fanta font, and that has several applications. For instance, we can do content augmentation. We can take an image with syntax and change the text content, the text transcription, but preserving the original style. So we only have qualitative results for that, but it can have many applications. So the conclusions of this last question is that first, we are able to transfer styles between syntax images learning from a single image because .NET is learning textual texture features. And second, that the end-to-end method we propose for selective strand transfer can have many other applications in other domains. For instance, we could also apply it as a data augmentation method for object detection. And this was joint work with Ali, who is over there, also a PhD candidate in this lab. Also a pleasure working with you. And it resulted on also in an ICDAR publication last year. So that was the first chapter. And now let's go with the second one. So, in this second chapter, we are working with social media images with an associated text, which in this case, it's going to be an associated caption. And we are going to see how we can exploit that captions to learn visual features, using them as self-supervision and applying them to multimodal image retrieval. So we have tons of images with associated text. For instance, in Wikipedia we have articles that contain images, or in Instagram we have millions of photos with associated caption and tags, or the same in Twitter or in Flickr. And from that data we can learn which relations users establish between images and text in that different social networks. And at the end, here what we are learning is to learn the relations that users establish between visual concepts and text when the data has a synergetic semantic meaning, right? When the image and the text have a similar semantics. So in this chapter, we are going to work with these three datasets. The first one, Web Vision, is a dataset containing Flickr and Google images with captions. The second one, InstaCities, is a dataset we create made by Instagram images associated to English-speaking cities and their captions. And the second one, it's similar but containing Instagram images associated with Barcelona and their captions. So in this chapter, I'm going to use semantic text embedding models. And we are going to experiment with text representation models oriented to generate representations, to learn representation of long text, such as LDA, Log2Vec, and also with word-level representation methods, such as Word2Vec, Globe, or FastText. And we are going to exploit a feature of these models, which is that they learn text representations with a semantic structure. For instance, operating with Word2Vec word representations, we can sum up the representations of mother and men and get the word representation of father. So they have these semantic structures, and you can perform arithmetics with them. So this is the methodology we propose. First, we are going to train these text representation models with the training text from social media, to ensure that we are learning representations for those specific social media words. And then we are going to train a CNN to embed images in that same text representation space by training it to embed an image in the same point as its associated caption it's embedded in. So at the end, we are going to end up with visual embedding and a textual embedding that can embed images and text respectively in the same space with semantic structure. So that allows us to apply it to image retrieval in a straightforward way. For instance, we can compute textual queries by combining word representations. We can sum up them, and then we point to a point in this embedding space and get the nearest images. And we can also apply that to multi-modal image retrieval, where queries are composed by a word and an image. So this is going to be trained. This is trained with social media data. So we are learning visual features associated to any word we can imagine. So for instance, we have some results, some abstract queries, I would say, and we see the visual features that people in Instagram associate with them in Instagram, right? So we see that in Instagram, people associate the word happy with images of people smiling, or the word Monday with coffee. And we can perform complex queries. So for instance, we see that people associate food and fast with images of hamburgers, or food and healthy with images of salads. And this is particularly good retrieving images related to topics that are common in social media. Like for instance, the net can distinguish between hairstyles of men and hairstyles of women, or it can distinguish between along the world. And we can also perform multimodal queries. So for instance, here, we're going to get an image similar to this sunset in the beach, or without the sunset. It also works doing that. So in here, we conducted a performance comparison of the different text representation methods in image by text retrieval. And we see that level methods such as word-to-vec and glove have superior results, and that's probably because of the data we are learning from, right? We are learning from images with associated captions, which in general are quite concise and even include hashtags associated to those images. And we publish those results in a NICCB workshop and also in a book chapter. So this method from learning from social media data has a huge potential. In here we see a TCNA plot which basically shows images where they are embedded in this join semantic space. So we can see, for instance, we have a cluster of food images, or we have a cluster of images related to beauty. And note that we can navigate all this space by using visual. So, as I said, this can have many different applications, because we can investigate with which visual concepts people relate in social media, which any word, right, any concept we can imagine. So they can have a lot of social and commercial applications. And here we research in one of them, and we are going to work with Instagram data related to Barcelona. So just training a word-to-vec model with the captions of this dataset, we see some applications it can have. For instance, if we inspect the words that people associate with healthy and restaurant, here we see some specific Barcelona restaurant names, right? So this can have an interest for the industry. And if similarly as we explained before, we train a visual embedding net to embed images in this word-to-vec space, for instance, that people associate the word breakfast with chocolate con churro images, or the word Poble Sec, which is a neighborhood of Barcelona, with these tapas images, which is a trendy thing to eat there. So I explained this application in Forum Touristic. Forum Touristic is a forum here in Barcelona to explain the latest technology and how they can be applied to the tourism industry. And I showed them how we could use these tools to analyze which concepts, both visual and textual concepts, people were associating with hotels, restaurants, or neighborhoods in Barcelona. And they seem pretty interested on it. So was doing during this presentation, I realized that most of the data I was learning from was data from tourists. And I thought that I could also use these tools to analyze the tourism in a city. So what I did was to do a language separate analysis. And I did the same analysis in English and in local languages, Spanish and Catalan, assuming that English publications were from tourists and publications in local languages were from locals. Here we have a plot of the percentage of publications mentioning each one of the Barcelona neighborhoods. Yeah, of course, in more touristic neighborhoods, you get more publications in English. So what I did here is to compute a representation of the captions in the data set which show a similarity with each one of the neighborhoods in Barcelona. And then I train, similarly as before, a CNN to embed images in that space, in this case using a ranking loss. So, say before, we can retrieve which images people, in this case people speaking or posting in the different languages, associate with each one of the neighborhoods in Barcelona. So in here we see that here in red we see the results for English people. So we see that with Poblesec they associate these images of tapas, but people speaking in local languages, Catalan and Spanish, they associate local gatherings or art galleries, right? So this is a tool that can be used to analyze the different behavior of different population groups in a city. And these experiments also resulted in a publication in an ECCB workshop. So then here, I want to show you how we can use this deep dream algorithm to analyze which kind of features this net is learning. Deep dream is written by Google, which hallucinates what a CNN sees in an image. So basically here we see this cloud's image, and if we apply a CNN trained with images on it, it starts hallucinating in animals in the clouds, because this ImageNet has been trained with many animal images. And if we apply the same, but with the net trained with Instagram data from Barcelona, we see that it's learning patterns related to typical tourist attractions in Barcelona. So for instance, we see patterns related with the Montjuïc Fountain or patterns related with Sagrada Familia. And if we apply this to other layers, we see other patterns. For instance, here we see patterns related to food, another hot topic in Instagram. Or in this other layer, we see patterns related to Football Club Barcelona, which is another hot topic in Instagram related to Barcelona. Okay, so that was all for the second chapter. Okay, going with the third chapter now. In this chapter, we are going to deal with image text and an additional modality, which is geolocation. And this is the three research questions we are going to answer. The first one is which one is the best method to learn with images from images with associated tags. So no locations used here. The sixth one is about how can we exploit jointly visual information and location information to improve image tagging performance. And the seventh, it's about how can we train a retrieval system to retrieve images related to a given tag and near to a given location. And we are going to see in this chapter which challenges using this additional location information comes with. So yeah, this is the first tag, location-sensitive image retrieval. So in here, for instance, we want to train a model to retrieve images related, but associated with a location. So for instance, we want to distinguish between temple images, Athens, and temple images. The second tag, location-sensitive image tagging, we want to jointly exploit visual information and location information for image tagging. So for instance, if we have this image of a generic mountain, let's say, and we know that it's located in Kathmandu in Nepal, it will be easier to predict the tag Himalayas. While if we know it's located in Berna, it would be easier to predict the tag Alps or Switzerland. So in this chapter we work with this dataset consisting, it's a large scale dataset consisting on 100 million images of Flickr with associated tags and geolocations. We're going to work with a large vocabulary of 100,000 tags and with locations represented as latitude and longitude normalized between 0 and 1. So this is the first step of our method. We are going to learn visual representation using the hashtags as supervision, right? And we are going to benchmark 3 different baselines to do that. The first one is multi-class classification, where we use a softmax activation and a cross-entropy loss. For the softmax activation, at each training iteration, we are going to select one random tag of the image in case it contains more than one, which is typical as the positive one. The second setup, multi-level classification, which set each tag as an independent classification problem with a sigma activation and a cross-entropy loss. And the third one, which is similar to the one I was using in the second chapter, it's a hashtag embedding regression, where we are going to train a net to regress its associated tag globe embedding. So results on location agnostic image retrieval and image tagging show that in both tags the multi-class classification method is the one performing best, with a huge difference actually. And that might seem counterintuitive because we have multiple tags per image, but it's consistent with results shown in other works, as the one I'm citing here, when we have a large number of tags. So once we have trained these visual representations, we are going to train the LocSens models. The LocSens model has as inputs triplets consisting on an image, a tag, and a location, which is here. It's hidden, but it's here. And remember, the location are coordinate, latitude, and longitude coordinates normalized between 0 and 1. And we are using pre-trained image and tag representations. So this model, it's going to map the 3 modalities to the same dimensionality. It's going to normalize them, concatenate them, and then we add a set of fully connected layers until we predict a triplet score. And we are going to train the model to score positive triplets, which exist in the dataset, higher than negative triplets, which we create. And we are going to train it with a ranking loss. So when we trained this model, we found out a problem, which is that basically the model was using location too much. It was relying too hardly on locations to rank triplets. So for instance, when we were retrieving images associated to a tag and near to a location, it was retrieving images always near to that location, but maybe not that associated with the tag. So we proposed two strategies to solve that. The first one, progressive fusion with location dropout. In here, what we do is, at the beginning of the training, we multiply the location representation by 0, and we introduce that modality progressively during training. So we keep scaling up this multiplying factor until it's 1. And we also apply a dropout here, so that the location information is not always available during training, so that the LocSens model still can discriminate between triplets based solely on image and tag information. The second strategy is location Gaussian sampling, where during training we are going to sample location from a 2D Gaussian distribution centered on the ground truth latitude and longitude, and with a variance that decreases during training. So at the beginning of the training, the variance will be very huge, will be 1, so the location will be not informative at all. But during the training, we reduce that variance, so the location starts being more informative. And that method also allows us to train models sensitive to different location granularities, because the variance of the Gaussian has a direct geographical distance interpretation. So those are some results, some location-sensitive image tagging, image retrieval, results. So we see that the model distinguishes between different temple images along the world. And it can also distinguish between concepts that are not so typical in the location. So for instance, it can distinguish between winter images in Berlin or in Chicago. Here we have some challenging results, where the query concepts does not exist in the query location. So for instance, if we retrieve beach images near Auckland, we get beach images from there. But if we try to retrieve beach images from Moscow, where there's not a beach nearby, we are going to retrieve images of people sunbathing, which is kind of semantically similar, right? And the same, if we try to retrieve ski images from Sydney, where you cannot ski, we are going to get like surf images, which is also kind of similar, right? To evaluate the location-sensitive image retrieval, what we do is consider images correct if they contain the query tag and they are near to the query location than a given threshold. And we evaluate the models at different location thresholds. So what we see here is that when we input the raw locations to the model, these models perform very good at fine-grained locations, but at expenses of a big drop on location-agnostic retrieval. And the proposed location balancing techniques allow us to train models with a better balance between retrieving images related to the query tag and near to the given location. Those are tagging results. And in here we see that the model generally analyzes visual and location information to predict tags. So for instance, in here we have this image, which we know is in London. And while a location agnostic model is predicting New York, San Francisco, Skyline as tags, the LocSens model is predicting Thames, London, Docklands, Skyline, right? So it's jointly interpreting both modalities to predict better contextualized tags. Or in this other example of a church image in Paris, a location agnostic model is predicting general tags such as church, cathedral, tower, London, while the LocSens model predicts architecture, church, Paris, Église, or even Montmartre, right? So it it predicts more informative and specific tags. In here we have results of an image with different fake locations. So for instance, if we have this sailing image and we know it's in Cuba, the model is going to predict tags such as ship, catamaran, ocean, Caribbean. But if the image is in Toronto, where you don't have an ocean or a sea nearby, it's going to predict lake, right? Or if it's in Barcelona, it's going to predict sea, velero, mar, Mallorca. This is the evaluation of the location-sensitive image tagging. So we see that the LocSens model outperformed the location-agnostic models in both accuracy and also in diversity, right? It predicts more diverse tags. So, and therefore, more informative tags. Okay, so some observations of this chapter is that the proposed model manages to perform both tags exploiting both modalities. And also we have identified this problem, which is that it relies too much on location for the triplet ranking. And we will have proposed two strategies to overcome that problem. In general, training networks that deal with different data modalities, it's a very challenging task. And there are recent works, like the two ones I'm citing here, which study how to deal with these modalities in similar ways as we have proposed in this work. Which, by the way, all this chapter was published this year in an ECCB paper. Okay, so going with the fourth and last chapter of this thesis. This is about multi-modal hate speech detection, which is basically trying to identify hate speech in publications formed by a text and an image. So unfortunately, on social media, we have publications as this one, where if you analyze jointly the image and the text, they result to be hate speech, right? So we are going to see if we can train models to jointly analyze both data modalities and detect hate speech. What is hate speech? There are many definitions for it, but in here, to get a fast understanding of it, we can enclose it in these terms here. Hate speech can be racism, can be sexism, can be homophobia, or can be religious-based hate. In publications formed by text and image, sometimes analyzing together both modalities is required to detect their hate speech, right? So you have to jointly interpret both the text and the image to detect their hate speech. So what we do in this work, it's we gather tweets consisting on a text and an image containing keywords that are susceptible to contain hate, and we'll label them using Amazon Mechanical Turk. So we are going to ask 3 workers to label each tweet in one of these 6 categories: not hate, racist, sexist, homophobic, religion-based, or other hate. And we are going to create this data set, right? We have 150,000 tweets formed by image and text. We also extract the image text in case there is one with the OCR, and we make this data set public. And we conduct some experiments with different models. This is the most simple model we try here. So we represent the image with a CNN. We also extract the image text and represent the image text and also the tweet text with an LSTM. We concatenate the representations of the 3, let's say, inputs. And we add a set of fully connected layers until we get a score, and we train everything for hate, not hate classification. This is a more complex model we try out. It's inspired in visual question answering works. And in here, what we propose is to learn kernels for the CNN dependent on textual representations, with the idea of giving the model explicit capacity to model textual and visual interactions. And we also train it for hate, non-hate classification. So those are the results we get. And despite the image modality is shown to be useful for hate speech classification, in here we have the top score for hate images, and in here the images with higher score for not hate. The multi-modal models, the ones using the 2 data modalities, image and text, cannot outperform unimodal models that only analyze text. And a reason for that is that the task is very challenging. The complexity of the multimodal relations we have to learn is very high, and they are very diverse as well. And probably we have a small set of multimodal hate speech examples overall. So how can we address these problems? Well, we can try to transfer knowledge from other tasks. For instance, we could try to pre-learn visual features from other data that are useful for this task. Or we could try to learn from social media interactions. In any case, it's a topic which a very, very high social, political, and research interest. And actually, since this paper that was published this year in Winter Conference, and we published the data set, it has got many interest, and some other works have been published in the same direction. Actually, just like a few months ago, Facebook opened a challenge about multimodal hate speech detection based on synthetic data. Okay, so that's all for my thesis content presentation. Now I wanted to conclude this defense, saying that during this PhD, these nearly 4 years, I've been able to work in many different tasks involving visual and textual data. I've been able to learn a lot and to see how the research has like real impact. And it has been a very grateful experience. Also, since this was an industrial PhD in EURECAD, I've been able to work in other projects related to my research. Here we have 2 examples. In here we train a fully convolutional network for face and hair segmentation for a private project in Eurecat. And in here we work on an aerial robot that's a drone for sewer inspection. It had a camera taking images of the sewers, and we train also an FCN to detect automatically scratches in the sewer, which also result on a publication. I also had the opportunity to collaborate with other researchers. For instance, in my stay in the University of Trento this year, I was working with Raul, a PhD student there, and he was working in image-to-image translation. So we combine our knowledges, my knowledge on image retrieval and his experience in image-to-image translation to use an image retrieval system to boost the performance of an image-to-image translation model. And yeah, from that project also a publication came out recently in ACM Multimedia. So also a pleasure working with you, Yahui. And yeah, and now I'm continue working in research, and I'm currently in Dublin working with Huawei in video action recognition. And that's all. Thank you. Diane, hello?